Today, I'd like to introduce gas chromatography, also known as GC. The picture on the right shows the Agilent 7890B GC system. We use this GC system in our lab to analyze environmental organic compounds. Gas chromatography is the separation of a mixture of compounds into individual components. GC is a common type of chromatography used in analytical chemistry for separating and analyzing compounds that can be vaporized without decomposition. So GC can be used to test the purity of a particular substance or separate different components of a mixture. In GC, the mobile phase is a carrier gas. Usually, it is an inert gas such as helium or an unreactive gas such as nitrogen. Carrier gas can sweep the analyte molecules through the column. After entering the column, different chemical constituents of a sample pass in the carrier phase at different rates depending on their various chemical and physical properties and their interaction with the column filling. Finally, they exit the end of the column at different times and enter the detector. In the detector, they are identified electronically, and the peaks of different compounds will be shown on the screen. Usually, the order of retention is mainly governed by boiling points. There are different detectors in GC. The most commonly used detectors are the flame ionization detector, FID, and the thermal conductivity detector, TCD. In FID, electrodes are placed adjacent to a flame filled by hydrogen or air near the exit of the column, and when carbon-containing compounds exit the column, they are pyrolyzed by the flame. As a result, FID is mainly used to analyze hydrocarbons and it is destructive to the analytes. TCD relies on the thermal conductivity of matter passing around a filament with a current traveling through it. So, TCD is non-selective and non-destructive to the analytes. Another detector is electron capture detector, also known as ECD. It uses a radioactive beta particle source to measure the degree of electron capture. ECD is mainly used to analyze molecules contains electronegative or withdrawing elements or functional groups like halogens. As a result, ECD can be used to analyze emerging contaminants like chlorinated compounds, and it is non-destructive to the analytes. Detectors should be chosen based on the characteristics of the target compounds. Quantification of environmental samples is complicated and different from pure samples because environmental matrices are complicated. They have not only our target compounds but also other compounds in them. So sample preparation is very important. For example, for liquid samples, liquid extraction and solid phase extraction can be used. For solid samples, accelerated solvent extraction and microwave-assisted extraction can be used to extract the target compounds from the matrix. After extraction, cleanup is necessary because we need to get rid of the compounds we don't need other than our target compounds. After sample preparation, the choice of detector and column is also important, and this is based on the characteristics of the analytes. Temperature program for target compounds or similar compounds can be found in literature, and we can make modifications based on the method mentioned in the literature. In order to accurately quantify the samples and monitor the recovery of the whole process, the choice of surrogate standards and internal standards is very important. They should share similar characteristics with our target compounds, and they should not present in the natural environment. Otherwise, they will interfere with our result. And the choice of the concentration is also very important because if the concentration of surrogate standards or internal standards is too high, they may hide the peaks of our target compounds. If they are too low, the quantification may not be accurate. For the calibration curve, we need to make sure that the concentration of our target compounds are in the range of the curve. I'm a PhD student at the University of Maryland, and I studied the concentration of polychlorinated biphenyls in stormwater sediments. I collected stormwater sediments in urban areas and used the microwave inspection to extract PCBs from the sediment samples. And in order to get rid of the other compounds that PCBs, I used alumina to clean up the samples. And then I used captain to wash the PCBs out from the aluminum color. Here, PCB extracts were developed in hexing, and I'm going to inject this sample into GC to quantify the PCBs.